Hi, I'm Pete Masterson, an engineer with Aearo. In our last video, Chirag showed us how to use a reduced frequency nomogram to determine the modulus of our materials and how geometry affects shape factor in an isolator's design. In this video, we will discuss how to use that information to determine an isolator's stiffness, also known as spring rate, and how that determines the natural frequency of the mechanical system in which it is placed. Spring rate, usually denoted by K, reflects the back force of the mount under deflection. An elastomeric isolator has a stiffness that depends upon two factors: the modulus of the material at a given temperature and frequency, and the geometry used in the design. The following equation shows how to determine the spring rate for a simple elastomeric cylinder. In the spring equation, you will notice the term E sub c. This is the corrected modulus for the material, which depends upon the modulus from the reduced frequency nomogram and the shape factor, both of which were discussed in video 1 of this series. The stiffness also depends upon the area under loading and the thickness of the cylinder. Spring rate can also be determined via finite element analysis for complex geometries. As you can see in the picture, a computer is used to break the model of the isolator down into small, easy-to-solve components, then tally the behavior of the components to determine the overall behavior of the part. Once spring rate K is known, we can then determine the natural frequency of the system. We typically use a single degree of freedom system to approximate the behavior of most systems. A single degree of freedom model involves a mass mounted on a spring which is connected to ground. The natural frequency of a single degree of freedom system is given by the equation F sub n is equal to the square root of K over m divided by 2 pi. Natural frequency is the fundamental characteristic of every spring mass system. It is the frequency at which very little energy input to the spring mass system will create an amplified output. The classic example of this is the Tacoma Narrows Bridge, which demonstrated catastrophic failure when a system was excited at its natural frequency. Likewise, in an electrical system, if we do not design the spring properly, the shock, vibration, or acoustics of that system will behave poorly. Be sure to watch part 3 of this video series, where we will discuss how to use natural frequency and stiffness to determine the isolation capability of our mounts. Thank you.